Hello. In the previous lecture, we discussed what is a group homomorphism and what are subgroups. Today, we want to study building blocks of a group as subgroups. And those building blocks means the smallest subgroups that contain a given element. That kind of groups we call cyclic groups. So the goal of this video is to study cyclic groups. But before that, let me briefly recall some of the statements that we have proved in the previous video. We defined what is a group homomorphism and what is a subgroup. Essentially, a group homomorphism is a function from one group to another that preserves the binary operation of these groups. Meaning, f from G to G prime is called a group homomorphism if for any pair of elements inside G, let's call them G1 and G2, f of G1 times G2 is the same as f of G1 times f of G2. Then we define what are subgroups, and subgroups are essentially subsets of a given group that form a group themselves by the given operation of the initial group. We proved a subgroup criterion. We proved these kind of results that I'm going to list right now. So for instance, we defined centralizer of an element, and that would be all the elements inside the group that commute with the given element G. So that we call the centralizer of the element G inside this group. We showed that this is a subgroup of G. We use this notation to indicate that it is a subgroup. This is a kind of inequality between a subset of a group and a group. That means that this is a subgroup of G. So again, we say H is a subgroup of G and we write it like this. The other thing that we proved is that the center of G, which means those elements of the group that commute with every element of the group. So those G's inside the group that commute with every other element, those we call that set we call the center of G, and it is again a subgroup of the group. It is the center of G. We proved that what we called the converse of subgroup criterion, and that is that if H is a subgroup, then it does contain the neutral element, and if X and Y belong to H, so does X times Y inverse. So if X and Y are inside H, then X times Y inverse is also inside H. The converse of this statement we call to be the subgroup criterion. So subgroup criterion says that if I give you a subset of a group, I tell you that it is not empty, and I tell you that for every pair of elements inside H, X times Y inverse is also inside H. So for X and Y inside H, I tell you that X times Y inverse is also inside H. This is enough, these two conditions, saying that it's not empty and saying that for every X and Y inside H, X times Y inverse is inside H. These conditions are enough to deduce that H is a subgroup of G. This is how we proved that the center is a subgroup, or centralizer is a subgroup, and so on. Then we defined, we showed that if F is a group homomorphism, then its image and kernel, we defined image and kernel of a group homomorphism, and we showed that image is always a subgroup of the codomain and kernel is always a subgroup of the domain. And let me quickly recall that kernel of a group homomorphism consists of those elements of the domain that are mapped to the neutral element of the codomain. We showed that this is a subgroup of G. We also discussed that if F is a group homomorphism, then F sends the neutral element of the domain to the neutral element of the codomain, and f of g inverse is the same as f of g inverse. So these are be categorized as basic properties of group homomorphisms. And we also discussed the following important example for every given group G written in multiplicative form and an arbitrary element small g inside the group. We can refine this kind of exponential map from the set of integers to the group G, which sends n to g to power n. And we discussed that this is indeed a group homomorphism. Now, using especially the last part, we can construct this group G little by little. We can add to it one step at a time, one element at a time. This is a point of view that we want to take right now. So we want to construct or generate a given group. But what does that mean? So let's say I give you a non-empty subset X of G. And I ask myself, what is the smallest subgroup of G which contains X? I forgot to write down X. What is the smallest subgroup of G which contains X? Is there any such smallest subgroup? Maybe there is no smallest subgroup. Maybe there are some subgroups that contain X, but we cannot compare them at all, and then there is no smallest one that contains X. What we will show is that indeed there is the smallest subgroup of G which contains a given non-empty set X. And we say that this subgroup is generated by X, and we denote it by this angle X. So open angle and close angle X. So this notation means the smallest subgroup that contains the non-empty set X. Of course, this notation would depend on on G. I mean, X is not just a set. X is a subset of this given group, and this notation means what is the smallest subgroup of G which contains this set X. And the claim is that there is such a subgroup, and we denote it by this angle X, close angle. Okay, so let's formulate the precise claim and prove it. So I'm given a group, and we are denoting its operation by dot, and X is a non-empty subset of G. In that case, there is a unique subgroup H of G with the following properties. First of all, X is a subset of H, so H contains X as a subset. Second, if I give you any other subgroup of G which contains X, then H should be a subset of it. So H is indeed the smallest subgroup of G which contains X, because it is contained in any other subgroup of G which contains X. Okay, so I'm interested in the following set then. I'm interested in all the subgroups of G which contains X. And I want to find the smallest one among these elements. Now, the first thing that we notice is that this is indeed a non-empty set. There is something there. What is that? Do we have a subgroup of G which contains X? Yes, of course, because G is a subgroup of itself, and it does contain X as a subset. So it is a non-empty collection. So G does belong to this sigma. So sigma is a non-empty collection of subgroups of G. So it does make sense to seek for the smallest element of sigma now. Okay, so what can that be? If we show that intersection of all the elements of sigma is still inside sigma, then that would be the smallest one. And that would be the unique smallest one. Okay, so that's what we are going to show. We are going to discuss that if I look at intersection of all the elements of sigma, okay, it's intersection of collection of subgroups. We have proved in the previous lecture that if I give you a family of subgroups and I intersect them, I end up getting another subgroup. So this intersection, if I call it H, is indeed another subgroup of G. So it is a subgroup of G. Now, this subgroup, my claim is that this subgroup does contain X as a subset. Why is that the case? So for every K that's subgroup of G, if X is a subset of K, then K is inside sigma. And from here, I can deduce that, okay, so let me see. Here is, this is the claim that I was making. For every K that I give you inside sigma, X is a subset of K. That's the definition of, this is what sigma is, collection of all the subgroups that contain X. Now I'm looking at the intersection of those elements, those subsets. Because every single one of them contains X as a subset, their intersection also contains X as a subset. So X is indeed a subset of the intersection of these Ks. But this intersection we call to be H. So X is a subset of this subgroup H. So X is a subset of H. Now, if I tell you, so this again, this implies that H itself is a subgroup and it contains H, it contains X, and in particular that implies that H is inside sigma. Now I want to tell you that every element of sigma contains, okay, so if I give you, so you see, what do I want to do? Let's not lose our sight, the sight of the goal. The sight of the goal is to present a subgroup that contains X as a subset, and if I give you another subgroup which contains X as a subset, then H is a subset of K. These are our goals. The existence part of H is the following, is this. Now, our claim is that this H satisfies those conditions. That's what I'm checking. I'm checking this and that. I wrote the first part, second and so on, but I explain the first part. I want to explain why X is a subset of H, and this is what I did. I said that for every K inside sigma, I have that X is a subset of K, and therefore X is a subset of the intersection of such Ks, which implies that X is a subset of H. So that gives us the first part. Now for the second part, I start with K, that's a subgroup of G, and it contains X as a subset. So this condition and this condition. But these two conditions imply that I'm in sigma. That's what I wrote over here. So having these two conditions implies that K is inside sigma. But that of course means that it is a term inside this intersection, and therefore H is a subset of that K. Okay, so now we have both of these conditions that we were looking for. This shows existence of H. Now next I'm going to discuss uniqueness of H. If I give you H prime, another subgroup that satisfies these properties, what does that mean? That means that H prime is a subgroup and it does contain X as a subset. But these two conditions is the definition of sigma. So knowing that H prime satisfies what we like implies that H prime is an element of sigma. Because again, X is a subset of H prime and H prime is a subgroup of G. But that means H is a subset of H prime because H was intersection of all the elements of sigma. In particular, it's a subset of H prime. And H itself, so H is a subset of H prime. But remember, one of the conditions of H prime was what? One of the conditions of H prime is the second one, that if I give you a subgroup and it contains X as a subset, then our set is supposed to be a subset of it. Now H prime is supposed to satisfy this. H is a subgroup of G, and it does contain X as a subset. Because H prime is supposed to satisfy the desired property, H prime should be a subset of H. Now, H is a subset of H prime is a subset of H. Altogether, we deduce that they are the same things. So at the end of the day, we are saying that this sigma that we introduced has a minimum, and the minimum is just intersection of all the elements. And therefore, we get the existence of the smallest subgroup that contains a given set. And that subgroup is called the group generated by X. Okay. When we start with a particular case, when the subset is finite, we often drop these curly brackets. Instead of writing down the group generated by, instead of writing the group generated by bunch of elements, G1, G2, Gn, we often just write the group generated by G1, G2, Gn with no curly brackets. In particular, if I give you a single element G, instead of writing the group generated by this element with a set with only one element G, we simply write down the group generated by G like this with no curly brackets. Okay? And such a group is called a cyclic subgroup. So a cyclic subgroup is a subgroup which is generated by a single element. Now, what I want to do in this video is to understand the structure of cyclic subgroups. What are the possible subgroups of a given cyclic subgroup, and this type of information. Okay, so here we define cyclic subgroups, but we can also talk about cyclic groups. What is a cyclic group? A group is called a cyclic group if it is cyclic subgroup of itself. Alternatively, we can say a group G is cyclic if it is generated by some element of the group. So if there is some element G inside the group, so that the smallest subgroup that contains this G is the entire group, then we call it a cyclic subgroup. Now, the next lemma actually gives us a concrete understanding of elements of a cyclic group. Okay, so what is it? So suppose that my group G is generated by the single element small g. Then what are the elements? Claim is that the elements are precisely powers of G, integer powers of G. So that's the cyclic group generated by G. Okay, let's see why that is the case. The first thing is that this side is a subgroup. Why is that the case? Why is that a subgroup? In the previous lecture, in the previous video, we discussed that this exponential map f from z to g that sends integer n to g to the n is indeed a group homomorphism. And therefore, its image is a subgroup of G. So image of f is a subgroup of G. But image of f is precisely this side. So this side is a subgroup of G then. So that is image of f. Now we notice that f of 1 is G to power 1, and that is G. And therefore, G does belong to this subgroup. Now, the group generated by G is the smallest subgroup which contains G. And this guy is a subgroup which contains G. Therefore, this is a subset of the right-hand side. So this is a subset of the right-hand side. Now I want to show equality. So far I have shown that this contains the cyclic group generated by G. So next we want to show that the other side of inclusion also holds. First, I'm going to show that for every non-negative integer n, g to the n is inside the cyclic group generated by G. Then I'm going to argue the same statement for non-negative integers, for non-positive integers. In order to show this claim, we are going to proceed by induction on n. The base of induction is rather easy because g to power 0 is the neutral element, and we have proved that neutral element belongs to every subgroup. In particular, neutral element belongs to the cyclic group generated by G. Okay, so that was the base of induction. Now I'm going to the induction step. What is induction step? Induction step says that I am going to assume my claim at step k. Next, I want to prove it for the next step, and that is step k plus 1. Okay, so if we can show this implication, then by induction we deduce that this claim is true for every non-negative integer n. We check the base case, we made the first step, and we are saying that after k step I can manage to go to the k plus 1 step, therefore I can go everywhere. That's the induction. Okay, so we start with the fact that the group generated by G is a subgroup, so it is closed under multiplication. G does belong to this subgroup. G to the k belongs to this subgroup because of the induction hypothesis. So we call this induction hypothesis. By the induction hypothesis, we have this part. By the fact that this is the cyclic group generated by G, we do know that G belongs to this subgroup. And being a subgroup means that it is closed under multiplication. It implies that it is closed under multiplication. Therefore, product of these two elements is still inside the group generated by G. And the product of these two elements is precisely G raised to power k plus 1. So this shows that e to the n, if n is a non-negative integer, belongs to the cyclic group generated by G. Now I'm going to discuss why the same statement is true for negative integers. So suppose n is indeed non-negative, but then I want to show that g to power negative n belongs to the same cyclic group. By part 1, we know g raised to power n belongs to this. Being a subgroup, we know inverse of every element is still inside this subgroup. Now g to the n is inside this subgroup, therefore g to the n inverse is still inside this subgroup. But we proved that g to the n inverse is the same as g raised to power negative n. And therefore, g to power negative n belongs to the group generated by G. By these two claims, we deduce that every integer power of G is an element of the group generated by G, and therefore we have the other side of inclusion. By this side of the inclusion and the other side that we have over here, we deduce that equality holds. Now we understand elements of cyclic groups. Every element of cyclic group generated by G is indeed a power, an integer power of G. Now, let's see some properties of cyclic groups and some examples and so on. Knowing that a group is generated by a single element, we can deduce that it is abelian. So cyclic groups are abelian. So let's see why this is the case. So I pick two elements inside the group, cyclic group generated by G, and I want to show that they commute with each other. We know that every element of G, if I pick X and Y inside this group, we know X is going to be a power of G, and Y is going to be a power of G. That we proved earlier. We showed that a cyclic group generated by G, all the elements or powers are integer powers of G. So X is G to the M, and Y is G to the N for some integers M and N. Now, when I compute X times Y, I get G to power M times G to the N, which is the same as G to power M plus N. When I compute Y times X, I get G to the N times G to the M, which is G to power N plus M, but integers are abelian, so I can write down M plus N. So it's equal to G to power M plus N. And they are the same. So this is equal to this. And therefore, X times Y is equal to Y times X. So every cyclic group is abelian. Now, next what we want to do is to study subgroups of a cyclic group. The following theorem is an important result. You will be using it later in other courses of algebra, and the idea is also crucial, so please pay attention to this theorem. Every subgroup of a cyclic group is cyclic. So every subgroup of a cyclic group is cyclic. So let's see how we can prove this. So suppose I'm given the cyclic group G. It's generated by an element small g, and H is a subgroup of group G. So all the elements of G are integer powers of small g that we proved earlier. Now I want to show that H is also generated by some element. Okay, let's separate the easy case. If H consists of only the neutral element, there is nothing to prove. It's generated by the neutral element. That's the smallest subgroup that contains the neutral element. So in that case, we are done. It is cyclic. It's generated by the neutral element. Now I'm going to assume that it's not the trivial subgroup, which means it's not just the neutral element. It contains something that is not the neutral element. So it contains some power of G, which is not the neutral element. For some L, that's a non-zero integer, G to the L belongs to H, and moreover, it's not the neutral element of G. Now, because H is a subgroup, inverse of that element also is inside H. And G to the L inverse, which is inside H, is nothing but G raised to power negative L. Now, either L is positive or negative L is positive. Considering that L is not zero, we can deduce that either L is positive or negative L is positive, and therefore there is some positive integer m where G to the m belongs to H. Now, among all such positive integers, I'm going to take the minimum one. So among all the integers that are positive and G to the m belongs to H, I take the minimum. Why is there such minimum? The reason is that this is a non-empty set. We just showed it. We showed that there is some such positive integer where G to the m belongs to H. And by the well-ordering principle, we know that if I give you a non-empty subset of positive integers, it has a minimum. And I'm going to call it minimum S. Okay, so S is the minimum of all positive integers where G to the m belongs to the subgroup H. Now, my claim is that H is indeed generated by this G to power S. Now, the first thing that we notice is that because S is inside this set, what does that mean? Because S is inside this set, that means that G to power S, I forgot to write down S over here, that means that G to power S is inside H. And of course, it also means that S is integer and S is positive. But now I'm focusing on this, that G to the S is inside H. Now, H is a subgroup, and therefore, it contains G to the S. It contains G to the S, and therefore, the smallest subgroup, the group generated by G to the S, is a subset of H. The smallest subgroup that contains G to the S is a subset of H. But we understand the elements of this guy. Elements of this guy are of the form G to the S raised to some integer power. So we deduce that every integer power of G to the S is an element of H. But G to the S raised to power k, we have proved in earlier videos that this is the same as g raised to power sk. And so every multiple of s power of g is inside H. Okay, so far we have this implication, this inclusion that the group generated by G to the S is a subset of H, and we interpreted this in this sense that every integer multiple of S power of G should be inside H. Now I want to show equality. I want to show that H is the subgroup generated by G to the S. Okay, so we have already showed one direction, that this is contained in H. I want to show the other way around. So I pick some element inside H, and I want to show that it belongs to this group. Okay, so it's enough to show that H is a subset of this, and we pick an element inside H, and I want to show that it belongs to the group generated by G to the S. Because H is an element of capital H, and capital H itself is a subgroup of the cyclic group generated by G, we do know that H is of the form small g raised to some integer power m. Now I'm going to divide m by s. I want to say that m is a multiple of s. So in order to show that, I'm going to divide m by s, and I'm going to argue that the remainder should be 0. Therefore, m is a multiple of s. If I show that m is a multiple of s, I'm done. That because every element inside the group generated by G to the S is nothing but an integer multiple power of so integer multiple of s, g raised to power that guy. Okay, so again, I'm going to take this m divided by s and get a quotient and a remainder using long division. So m is s times the quotient plus the remainder, and the remainder is a non-negative integer that is strictly less than s. We have divided m by s. Now, g to the m is g raised to power sq plus r, and it is supposed to be inside H. We have proved that any integer power of s, when I raise g to that power, it belongs to H. In particular, g raised to power sq is an element of H. Okay, so this part is an element of H. The whole thing is an element of H. That means that g raised to power r should be inside H. So let's make it precise. Because these two elements, both of them are inside H, g to the m times inverse of this is also inside H. But I can simplify this and write it as g raised to power m minus sq. And m minus sq is nothing but r, because m is sq plus r. So from this computation, we get that g raised to power r is inside H. But how can that be? Remember, s was the minimum of all positive integers where g to the m is inside H. Now, I'm telling you that g to the r is inside H, and r is strictly less than s. How can that be? This is what's supposed to be minimum among positive integers with this property. The only possibility is that r is not positive integer. So from these I can deduce, from this and this, I deduce that r is not a positive integer. So r is indeed an integer, therefore it should be a non-positive integer. But r is also non-negative. So r is non-positive and non-negative, so it is 0. So the remainder is 0, which means that g to the m is nothing but g raised to power sq. That's an integer multiple of s, which means it is in the group generated by G to the S. Remember, the group generated by G to the S consists of g raised to power some integer multiple of s. Now, this sq is an integer multiple of s. Therefore, this belongs to the subgroup generated by g to the s. Now, this gives us the claim, and that completes the proof of this theorem. Every subgroup of a cyclic group is cyclic. That is what we proved here. This is an important theorem. Please try to remember how we proved it and how you try to use it in the questions that you will be asked later. As an application, we immediately get the following corollary about the group of integers under addition. Every subgroup of the group of integers is of the form nz for some non-negative integer z, for non-negative integer n. So every subgroup of z consists of multiples of some non-negative integer n. So why is that the case? First thing that we discuss is that the group of integers under addition is indeed a cyclic group. But before that, in order to avoid this confusion, let's recall that in an additive setting, instead of writing g to the m, we simply write mg. So in additive setting, we don't use this exponential notation, but we rather use m times g. And every integer in z is of the form m times 1. So a subgroup of gn plus, which is generated by g, so under addition, is not g raised to power m. So don't make this confusion. Please don't make this confusion. When you are using plus, do not write g to the m for the cyclic group generated by g. When you are using plus, the cyclic group generated by g consists of elements of the form mg, where m ranges inside the group of integers, the set of integer numbers. So again, let me repeat this. I cannot overemphasize this. Please do not make this mistake. When we are using the plus notation, the cyclic group generated by an element consists of integer multiples of g. We use this notation instead of g raised to power m. Therefore, as a particular case of this, we see that the subgroup of z, which is generated by n, is the set of integer multiples of n that we also denote by nz. So all these nz's are indeed subgroups of z. This we have discussed earlier. Moreover, if I start with integer 1, I'm getting all the integers out of the group generated by 1. Therefore, the cyclic subgroup of z that's generated by 1 is the entire z, and so it is a cyclic subgroup. It is a cyclic group. And so by the previous theorem, every subgroup of z is cyclic. Now I give you a subgroup of z. We know that it is cyclic, therefore it's generated by some integer n. That means h is nz. Now notice that because h is a subgroup, it is also closed under taking negation. And moreover, integer multiples of n are the same as integer multiples of negative n. So nz is the same as negative nz. And so it is the same as the absolute value of nz. So without lots of generality, I can assume that this n itself is non-negative, or absolute value of n is definitely non-negative. So that completes the proof. This shows that every subgroup is of the form some non-negative integer times z. So that those are all the subgroups of the group of integers under addition. Now, the next theorem also plays an important role in understanding cyclic groups in general and elements of an arbitrary group. So suppose I give you a group and I give you an element of this group. Now, there is a unique non-negative integer d So there is a unique non-negative integer d with the following property. First of all, g to the d is the neutral element. Second, if g to the n is the neutral element, then d divides n. Okay, so I can write it in this format if and only if g to the n is the neutral element if and only if n is a multiple of d. So it gives us a complete understanding of those integers that's going to give us the neutral element as I raise g to that power. So g to the n is the neutral element of the group precisely when n is a multiple of d. If this d is a non-zero integer, it's a positive integer, then we call it the order of g, the order of the element g. If it is 0, then we call the order of g to be infinity. I'm going to write this down after we go through the proof of this theorem. But I wanted to emphasize on this for you to pay more attention to this theorem, because order of elements play an important role in this course and beyond that. Okay, so let's recall that this exponential function is indeed a group homomorphism. So f from z to g that sends an integer n to g to the n is a group homomorphism. And therefore, its kernel is a subgroup of the domain. That means it's a subgroup of z. Now, in the previous corollary, we proved that every subgroup of z is indeed of the form dz for some non-negative integer d. So by the previous corollary, kernel of f is of the form d times z for some non-negative integer d. What does that mean? Let's try to make it concrete. Kernel of f means the following. What are the integers so that when I raise g to power n, I get the neutral element? This is exactly the set of integers we were interested in and we were looking for. And that's captured in the kernel of f. Remember, f sends n to g to the n. Kernel of f means what are these n's that give us so that f of n is the neutral element. But this is f of n. This is f of n. So I'm asking, what are those integers so that g to the n is the neutral element? And the answer is that it is d times z. These are integer multiples of d for some non-negative integer d. So again, that means g to the n is the neutral element if and only if d divides n. Okay, this shows existence of such a non-negative integer, but at the same time, it immediately can help us to show uniqueness. Okay, so let's argue why there is a uniqueness. Suppose d prime is another such non-negative integer. What does that mean? This means that this d prime satisfies the same implications. In particular, g to power d prime is also the neutral element because d prime divides d prime. But now if I use this property for d, not d prime, I know g to power d prime is the neutral element. Therefore, d should divide d prime. Now I argue the other way around. I know g to the d is the neutral element, but d prime is supposed to satisfy the same implication. Therefore, d prime divides d. Now, d and d prime, both of them are non-negative integers. Both of them divide the other one. For instance, if d is 0, knowing that d prime divides it, I can deduce that d prime is also 0. Therefore, they are equal. If d prime is 0, knowing that d divides it, I can deduce that, knowing that d prime divides d, I deduce that d is a multiple of d prime. and therefore D is 0 as well. So again, we get equality. Now, if neither of them are 0, oh, this is also non-zero, I should have said. If both of them are non-zero, then both of them are positive. Remember, they were non-negative integers. And therefore, knowing that D divides D prime implies D prime is at least D. Knowing that D prime divides D implies that D is at least D prime. And from there, we deduce that they are equal. So now, this unique non-negative integer D that we got here is called the order of G, as long as it is non-zero. If it is 0, we say that the order of G is infinity. An element that has finite order is called a torsion element. Let me write this here. If order of G is finite, is not infinity, we say G is torsion. Otherwise, we say G is non-torsion. Okay, so now I want to understand finite cyclic groups a bit better. Let's start by listing all the elements of a finite cyclic group. Okay, so suppose I start with a group, a cyclic group that's generated by G, and I tell you that this element has order D. Now, what can I say about the group generated by G? What can I say about the elements of this group? So if the D is finite, the claim is that these are all the elements, and I get precisely D elements, and these are the neutral element, G squared, till we reach to G to power D minus 1. And these are distinct elements of this group. In particular, the group generated by G has precisely D elements if the order of G is D. If the order of G is infinity, then all the powers, all the distinct powers of G are distinct. So G to the I is different from G to the J if I is not J. In either case, we see that the cardinality of the cyclic group generated by G is the same as order of the group G. That's why for an arbitrary group capital G, the cardinality of G is called order of this group. So when we say order of a group, it means the cardinality of this group. And what we are proving right now is that the order of a cyclic group generated by an element G is the same as the order of the element G. So it's a kind of abuse of the word order, but the nice thing is that they are compatible with each other. That's the nice thing about this theorem. It tells us that the order of the element G is the same as the order of the cyclic group generated by G. Okay, let's try to prove this. Let's start with the finite case. Because of the definition of order, and D is finite, we deduce that G to the N is the neutral element precisely when N is a multiple of D, the order of this group, the order of this element. Okay, and remember, D is also positive. Now, non-negative, I should have said actually. Now, what do I want to do? I want to say that then the cyclic group is actually this one. Remember, if D is 0, there is, if D, order can never be, the order is always positive. So yeah, so sorry for that, order is positive. Now, I want to show that every element of the cyclic group is among these ones, and these are distinct. So let's start by showing that every element of the cyclic group is among these ones. Okay, so I start with an element of this, but we know every element of this group is of the form g raised to power n for some integer n. So I pick this element n, and I want to argue that g to the n belongs to this set. What I will do is that I'm going to divide n by the order d. So I'm going to divide n by d, divide n by d, get a quotient q and a remainder r, and then that means I'm writing n as this order d times the quotient q plus the remainder r. And r being a remainder is a non-negative integer which is strictly less than the order d. Now, g to the n, which is this arbitrary element of this cyclic group that I've picked, is, because n is of the form dq plus r, g to the n is g raised to power dq plus r. Now, we know that g raised to power of summation of two integers is product of these powers of g, so this is g raised to power dq times g raised to power r. Now, dq is an integer multiple of d, and we know that g raised to some integer multiple of d is the neutral element. So g raised to power dq is the neutral element. Okay, so the whole product would be equal to the neutral element times g raised to power r. Again, because d divides dq, of course. And neutral element times anything doesn't change that, so it is g to the r, and r is an integer in this range, which means g to the r is either the neutral element or g to power 1 or g to power 2 till we reach to g raised to power d minus 1. So these are all the possible elements that g to the n can be. So we showed that the cyclic group generated by g is a subset of this set. And of course, I have the other way around because all these are powers of g, so I have the other inclusion. Altogether, we get equality of these sets. The cyclic group generated by g, if the element g has order d, is the group consisting, is the set consisting of the elements neutral element, g squared, g to power d minus 1. Now I want to argue why these elements are distinct. They cannot be the same. That's what I want to show. So I picked two powers, I is strictly less than j, and both of them non-negative is strictly less than d, and I want to show that g to the I is different from g to the j. Now suppose that it's not the case. We got unlucky and g to the I happen to be the same as g to the j, when even though I is strictly less than j and it's strictly less than d, and they are both non-negative. What we can do is kind of cancel out this g to the I from both sides. Canceling out means we are multiplying by the inverse of this element. So let's multiply by the inverse of this element, and we end up getting, so this side we end up getting the neutral element, and in the other side we end up getting g raised to power j minus I. Now, j minus I, j minus I. J minus I is a positive integer. J is less than d. I'm subtracting something non-negative. J minus I is strictly less than d. But that's not possible. Remember, an integer power of g is neutral element if and only if that integer is a multiple of d. Now, g raised to power j minus I is the neutral element. Therefore, the order of g should divide j minus I. But that's not possible. Again, remember, j minus I is positive. and it is at most j, which is strictly less than d. There is no integer multiple of d from 0 to d strictly more than 0, strictly less than d. There is no multiple of d in this range. Therefore, that's a contradiction, which means that all these elements are distinct. In particular, the cardinality of this set is precisely d. And so the cyclic group generated by an element of order d has d elements. Now, what happens if d is infinity? In that case, the way that we define order, that means that we know g to the n is the neutral element if and only if n is 0. The only element, the only power of g that goes back to the neutral element is the power 0. As soon as I go away from 0, I cannot go back to the neutral element. Okay, so now I want to claim, I want to show that all the distinct powers of g are distinct. So suppose that g to the I is the same as g to the j for some integers I and j. Again, we are going to cancel out one side. We multiply, let's say, both sides by g to power negative j. We end up getting that this side is going to be g to power I minus j, and this side is the neutral element. So we end up getting that g to power I minus j, which is an integer, is the neutral element. But we showed, we have this condition that the only integer power of g that's the neutral element is the power 0. That means I minus j is 0, and therefore I is j. We showed the contrapositive of the statement that if I is not j, then g to power I is not g to power j, so that implies the contrapositive as well. Now all of these gi's are distinct as I ranges in the integers, therefore the cardinality of this set is infinity. So altogether we see that if order of g is infinity, the cardinality of the group generated by g is infinity. If order is d, the cardinality of the group generated by g is d. So in either case, we see that the cardinality of the cyclic group generated by g is equal to the order of the element g. Okay, so now we have an understanding of cardinality of cyclic groups. We have an understanding of elements of cyclic groups. Next, we want to investigate and understand subgroups of cyclic groups a bit better. This understanding of cyclic subgroups of cyclic subgroups will be important when you study rings as well, but more importantly when you study Galois theory, especially finite fields. Then understanding cyclic groups play an important role there. Okay, but before I get to subgroups of cyclic subgroups, let's try to understand order of all the elements of a given cyclic group. So I give you a finite cyclic group. I tell you that it's generated by an element of order n. Then I give you another element of this cyclic group, and I ask you, what is order of this element? This theorem gives us a formula, an important formula. This is extremely useful. We use it again and again, so please pay attention to this theorem. So if order of g is n, then order of g to the n is a divisor of n, and it is precisely n over the greatest common divisor of n and m. So let's again go over this. If order of g is n, and it is a finite number, then order of g to the m for every integer m, no matter what you pick, is n over the greatest common divisor of n and m. Okay, so let's try to prove this. Let's try to first recall what it means that order of g is n. This part is extremely important. You have to feel at home at it with this statement. So when we say order of G is n, and it is a finite number, this means the following implication, the following if and only if phenomena. That G raised to power k is the neutral element if and only if n divides k. Knowing that order of G is n means, and knowing that it is a finite number means, that G to the k is the neutral element precisely when k is an integer multiple of n. Okay, now I want to understand what is order of G to the m. So I need to understand under what condition Gm raised to power L is the neutral element. So again, with the same phenomena, with the same understanding over here, in order to find order of an element, I need to understand when I raise it to what kind of integers I end up getting the neutral element. So as soon as we answer that, we can understand what is order of G. Now I want to understand what is order of G to the m. So I need to raise G to the m, G to the m. I raise this guy to some integer power. And I seek for a nice condition under which I end up getting the neutral element. Now, G to the m raised to power L is the neutral element if and only if this side is G raised to power ml. Okay, so this happens if and only if G raised to power ml is the neutral element. Now, we know that some power of G is the neutral element precisely when the order of G divides the power. So this happens precisely when the order of G divides ml. The order of G is n, so this holds if and only if n divides the power that you're taking. Now, n and m have some common divisor. I can get rid of that. I get rid of the common divisor because that part is not going to play an important role. I'm getting rid of the common divisor, and this n divides this product precisely when I get rid of the common divisor, this fraction divides this fraction times L. Now, the nice thing is that when I get rid of the common divisor, that's called the common divisor D, when I get rid of the common divisor by passing to these quotients, I end up getting two integers that are co-prime. That's one of the main properties of the greatest common divisor that we discussed earlier. If D is GCD of n and m, then n over d and m over d are co-prime. Now, this integer and this one are co-prime. This divides product of this guy and L. It should ring a bell, and that should be Euclid's lemma. By Euclid's lemma, and the fact that n over d divides product of m over d times L, and n over d and m over d are co-prime. So they have nothing, no multiplicative factor in common. So this one is redundant. I can drop it. That's what Euclid's lemma tells us. Euclid has told us that if an element divides product of two elements, and this element has nothing in common with one of the factors, then that factor is redundant. I can just drop it. GCD of n over d and m over d is 1. They have no common factor. So whenever n over d divides this product, n over d divides L. Altogether, what did we get? We said that G to the m raised to power L is the neutral element precisely when n over d divides it. So that means n over d is the order of G to the m. Okay, so remember, of course, when n over d divides L, then n over d divides this product. So we have if and only if. So altogether, we have that if G to the m raised to power L is the neutral element, then that happens precisely when n over d divides L. That's the definition of order, as we discussed over here. That means that the order of G to the m is this integer. And remember, these is the greatest common divisor of n and m that completes the proof of this theorem. Again, let me emphasize, this is an extremely important theorem. You need to know this. You need to go over the proof, make sure that you understand the proof very well, and you will be given some homework assignments, and then you have to work with this theorem further. So again, let's go over this. Order of g to the m is equal to order of g. This is order of g over the GCD of order of g and m. Okay, so this is an important equation. Please pay attention to this. Okay, now, using this result, we can understand other generators of a cyclic group immediately. Suppose that I give you an element of finite order, and I tell you that g to the m generates the same group. What can I say about m? And this corollary says that this equality holds exactly when, if and only if, m and n are co-prime. So g to the m generates the same cyclic group precisely when m and n are co-prime. And therefore, a cyclic group of order n, of cardinality n, has phi of n generators. So when I say generators, I mean what are the elements that generate this cyclic group? And we are finding out that there are precisely Euler phi function of n of that many elements generate G. Okay, let's go through the proof. First thing first, G to the m is an element of the cyclic group, and therefore the cyclic group generated by G to the m is of course a subgroup of the cyclic group generated by G. And cyclic group generated by G is a finite group because it has order D, order of G is finite, and therefore it has the same cardinality as the order of G. It's a finite set. So this equality holds, because it's a subset of this one, and this is finite, equality holds precisely when they have the same cardinality. So the set, the group generated by G to the m is equal to the group generated by G precisely when they have the same cardinality. Now I'm in the realm of understanding orders, because we understand that the cardinality of the group generated by G to the m is the same as the order of the generator, which is G to the m. Similarly, cardinality of the group generated by G is the order of the element G. So the order of the element G, which is n, is the cardinality of this group, and cardinality of this group is the order of G, which is n, divided by GCD of n and m. Now, this equality holds, so this equality holds if and only if they have the same cardinality, but cardinality of this side is n over the GCD of n and m, and cardinality of this side is n. So this equality holds if and only if we have this one. And I can cancel out n, and then I get that this holds precisely when m and n are co-prime. That completes the first part of the proof. Now I want to show that there are precisely phi n generators, but we proved that the group generated by G consists of these elements, and these are all distinct. Now, when we say number of generators of this, it means I have to ask myself, is this a generator? Is this a generator? Is this a... So I have to look for integers in this range, and then I look at G to the m, and I ask myself, is G to the m a generator? And we prove that G to the m is a generator precisely when m is co-prime with n. So the number of generators is the same as the number of integers in this range that are co-prime with n and that by definition is Euler phi function of it. So a cyclic group of order n, so again, remember, order of a group is the same as its cardinality. So a cyclic group of order n has phi of n generators. Now, remember, a cyclic group, all the subgroups of a cyclic group are cyclic. So in the next lemma, I'm going to focus on cyclic subgroups of a given cyclic group, and I want to understand under what condition they are equal. In order to understand when they are equal, in fact, I will try to find a kind of a canonical generator for a given cyclic subgroup. So what do I mean by this canonical word that I'm phrasing? Don't get afraid of this word, forget about it, and look at this statement. You will get a better understanding of this word that I used maybe later. So suppose G is a finite order element, and suppose its order is n, and I give you some integer a, then the cyclic group generated by G to the a is the same as the cyclic group generated by the GCD of a and n. So all of a sudden, instead of taking an arbitrary integer, I'm working with a positive divisor of n. So that's what I mean by a canonical. So every cyclic subgroup of the group generated by G is generated by G raised to some positive divisor of n. Okay, non-negative divisor of n. Actually, positive divisor of n is okay. Okay, so again, if G is of finite order, order n, then every cyclic subgroup, every cyclic subgroup of the group generated by G is generated by G raised to some positive divisor, a positive divisor power of G. Positive divisor of n, positive divisor of order of G is the power. Okay, that's the key. We are going to come back to this lemma again, use it to describe all the subgroups of a given cyclic group, finite cyclic group. Okay, let's see why this is the case. Because D is the GCD of A and N, D definitely divides A. Therefore, because A is an integer multiple of D, G to D, so that means A is an integer multiple of D, therefore G raised to power A is G raised to power D raised to some integer power, which means it does belong to the cyclic group generated by G to the D. This element is inside this group. That implies the cyclic group generated by this is a subset of this group, because that one is going to be the smallest subgroup that contains G to the A. Therefore, this guy is a subset of the group generated by G to the D, because this is an element here. G to the A is the group generated by G to the A would be a subset of the group generated by G to the D. Now I want to deduce the other way around. But in order to show the other way around, instead of showing the other implication, I'm going to argue that these groups have the same cardinality. And because one of them is a subset of the other one, I get equality. Okay, I'm going to look at cardinality of this group. Cardinality of a cyclic group is the same as the order of a generator. So it's order of G to the A. Now, order of a power of G is order of G divided by GCD. Order of G is n, so this is the same as order of G divided by GCD of order and the power that I'm picking. GCD of n and A, we defined it to be T, so that means the cardinality of this group is the same as n over D. Now, similarly, the cardinality of the cyclic group generated by G to power D, by the same argument, is the same as order of G to the D, and that is order of G divided by GCD of order of G and D, the power that I'm picking. But remember, D divides N. D is the greatest common divisor of N and A, therefore D divides N. And so GCD of N and D is D. D is a positive divisor of N, therefore the greatest common divisor of N and D is D. So from here I deduce that it is also N over D. This is a subgroup of this, as we see here, and they have the same cardinality, finite cardinality. So equality holds, so they are the same subgroups. Now that we have a kind of canonical choice of generators for subgroups, I can describe all the subgroups of cyclic groups. Sometimes this is called classification of subgroups of cyclic groups. This is an extremely important result, maybe the most important result in this video. So suppose I give you a cyclic group generated by G, and I tell you that it has n elements. Then every subgroup of G is of the form a cyclic group that's generated by G to the M, where M is a positive divisor of the cardinality of the group. So every positive divisor of N gives us a subgroup. Now, an important fact is that if I give you two subgroups of this cyclic group, if they have the same cardinality, all of a sudden they are the same groups. So cardinality of subgroups uniquely determine the subgroup. Now, finally, if I tell you that D divides N and its positive divisor, then there is a unique subgroup of G which has cardinality D. So there is a bijection between positive divisors of N and subgroups of G. Moreover, one thing that I can add to this, that if, maybe I write it in blue, that if D1 divides D2 and they are positive divisors of N, then the subgroup that we get for D1 is a subset, is a subgroup of the one that we get for D2. So what I'm saying is that this divisibility tells us inclusion. We'll see this in the proof, but I did not write it here, so maybe I will include it later in the lecture notes as well. So the subgroup, so every subgroup, or the unique subgroup that has cardinality D1, let's denote that. So if this is the case, okay, or maybe I can say it like this. If cardinality of H1 divides cardinality of H2, and H1 and H2, both of them are subgroups of this cyclic group, then H1 is a subgroup of H2. So if I know the cardinality divides, I can deduce that it's a subset. This is a particular case of cyclic groups. This fails miserably for a group that's not cyclic. Okay, this is in fact true precisely when the group is cyclic. But we are not going to discuss the if and only if part. Maybe in a homework assignment later. But now I'm not going to discuss it. Okay, let's start with the first part, that every subgroup of G is of the form cyclic group generated by G to the M, where M is a positive divisor of N. We have already proved that every cyclic subgroup of a cyclic group is already cyclic. So if I give you a cyclic subgroup of the group generated by G, it's going to be cyclic. So if I give you H a subgroup of G, then it is cyclic. It's generated by one element, but every element of G is of the form G raised to power A. So H is of the form cyclic group generated by G to the A for some integer A. A priori, it's not clear whether or not A is a positive divisor of N. But in the previous lemma, we proved that the cyclic group generated by A is the same as the cyclic group generated by G raised to power the GCD of A and N. Therefore, this H, which is the cyclic group generated by G to the A, is the same as the cyclic group generated by G raised to power GCD of N and A, which is a positive divisor. This is a positive divisor of N. Therefore, every subgroup of G is of the form cyclic group generated by G to the M, where M is a positive divisor of N. Okay, so this shows part one. Now, if I tell you that by part one, you know every subgroup is of the form G raised to power M1 for some MIs that are positive divisors of N. So H2 is also G to power M2, where both M1 and M2 are positive divisors of N. Now, if I tell you that they have the same cardinality, we know cardinality of HI is the same as the order of its generator, and that is N is the order of G divided by the GCD of N and MI. But remember, MI divides N. Therefore, it is N over MI. Because I'm assuming that they have the same cardinality in part B, from here I can deduce that M1 is M2 because of this equality. Now, M1 is M2 implies that they have the same generator. That means H1 is H2. So this implies part 2. But let me also emphasize this part, which can be viewed as a strengthening of part B, part 2. So let me see how, let's explain how we can get that part with the same argument. So if instead of writing this one, I'm going to write it over here. So instead of this part, let's continue over here. So if cardinality of H1 divides cardinality of H2 using the star, this is star, we deduce that N over M1 divides N over M2. That means M2 divides M1. So M1 is an integer multiple of M2. So from here, you can deduce that G raised to power M1 is itself in the group generated by G raised to power M2. And therefore, the group generated by G raised to power M1 is a subset of the group generated by G raised to power M2, which means H1 is a subset of H2. And that's exactly what I claimed. So if cardinality of H1 divides cardinality of H2, and they are subgroups of a finite cyclic group, then H1 is a subset of H2. Okay, so in part 2, we are claiming that if equality holds, then equality over here holds. But now I'm showing even a bit more than that. If cardinality of this one divides cardinality of the other one, then H1 is a subset of H2. Okay, so now we showed this strengthening of part 2. We discussed part 2 as well. And now finally, I want to show that if D is a positive divisor, then there is a unique subgroup of G that has cardinality D, and therefore there is a bijection between positive divisors of N, and subgroups of G. So suppose I give you a positive divisor of G. I want to give you a cyclic subgroup that has cardinality D. We have already discussed that if I start with G to power M and M divides N, then the cardinality is N over M. I want to make this into D. So it's enough to choose M to be N over D. So if I take G and raise it to power N over D, remember D is a divisor of N and D is positive, so it does make sense to talk about N over D. I take G, raise it to power N over D, and I look at the cyclic group generated by this. Cardinality of this group is, because N over D is a divisor of N as well, it's going to be N divided by, remember, N is the order of G. It's N over the N over D because N over D divides it. And that is precisely D. So we end up getting a cyclic group that has order D, but we have already proved that if I give you two cyclic groups and they have the same cardinality, two cyclic subgroups and they have the same cardinality, then they are the same subgroups. That implies the uniqueness. So we showed the existence of a subgroup that has cardinality D, and the uniqueness follows from the second part, which says that having the cardinal, if two subgroups have the same cardinality, then they are equal. So altogether, we get this concrete bijection between subgroups of a cyclic group of order N, cardinality N or order N, and positive divisors of N. So we got this bijection between this. Okay, so as I pointed out, this correspondence between subgroups of a finite cyclic group and positive divisors of N plays an important role in finite field theory. Hopefully at some point you will learn about it. But it is also crucial for our course because cyclic groups can be viewed as building blocks of an arbitrary group. So we often use these techniques in order to understand behavior of an given element in an arbitrary group G. We'll continue with understanding group isomorphisms in the next video. For now.